Numbers are everywhere, from the moment we wake up and check the time on our alarm clocks, to the prices we see in stores, and even the numbers on street signs guiding us on our way. We use them to count, measure, and track things. Numbers help us keep track of everything from the groceries we buy to the data we analyze in scientific research. But have you ever thought about what a number system is? It's more than just a collection of symbols. It's a fundamental part of how we understand and interact with the world. A number system is like a set of rules. These rules define how we write numbers, how we perform calculations, and how we interpret numerical information. These rules tell us how to write and use numbers. Whether we're jotting down a phone number, calculating a budget, or using an abacus, we're relying on these rules. Imagine a world without a number system. It would be chaotic and confusing, with no way to label or quantify anything. It would be very difficult to communicate quantities, wouldn't it? Everyday tasks like shopping or even learning in school would become incredibly challenging. That's why we have number systems. They provide a structured way to understand and communicate numerical information. They help us organize and understand the world around us. From organizing data in charts and graphs to solving everyday problems, number systems are essential. In this chapter, we will explore different types of numbers and their properties. We'll delve into the fascinating characteristics that make each type unique. Get ready to dive into the fascinating world of number systems. This journey will be both educational and exciting. This journey will take us through the familiar territory of natural numbers and whole numbers. We'll start with the basics and build our understanding from there. We will then venture into the world of negative numbers with integers. Understanding these will help us grasp more complex concepts. Next, we will learn about rational numbers, which include fractions. These numbers are crucial for understanding parts of a whole. Finally, we will discover the intriguing world of irrational numbers. These numbers, like pi and 2, have unique properties that make them fascinating to study. Let's begin with the most basic type of numbers, natural numbers. These are the numbers we use for counting. 1, 2, 3, 4, and so on are natural numbers. They start from 1 and go on infinitely. Now, what if we add 0 to the set of natural numbers? We get whole numbers. Whole numbers include all natural numbers and 0, so 0, 1, 2, 3, 4 are all whole numbers. We use natural numbers and whole numbers in our everyday lives. For instance, we use them to count objects, measure lengths, or keep track of scores in a game. They are the building blocks of our understanding of numbers. As we progressed, we needed numbers to represent values less than 0. This is where integers come in. Integers include whole numbers and their negative counterparts. So -3, -2, -1, 0, 1, 2, 3 are all integers. Imagine a number line. Integers extend the number line to the left of 0, encompassing negative values. This expansion allows us to represent concepts like temperatures below freezing point, debts, or losses in a game. Integers are crucial for solving various mathematical problems. They help us perform operations like addition, subtraction, multiplication, and division with a wider range of numbers. Rational numbers are numbers that can be expressed as a fraction, where the numerator and denominator are both integers. The denominator cannot be 0. For example, 1/2, 3/4, -2/5, and 7 are all rational numbers. The word rational comes from ratio. Rational numbers represent a part of a whole or a ratio between two integers. They can be represented on the number line and are used extensively in various fields, including finance, science, and engineering. We often encounter rational numbers in our daily lives. Think about dividing a pizza or sharing a bar of chocolate. These actions involve rational numbers. Section 5. Irrational numbers. A new world of numbers. Now let's explore a fascinating category of numbers called irrational numbers. These numbers cannot be expressed as a simple fraction of two integers. Their decimal representations are non-terminating and non-repeating. One of the most famous irrational numbers is pi, which is approximately 3.14159, but continues infinitely without repeating. Another example is the square root of 2, which is approximately 1.41421. and also goes on infinitely without a repeating pattern. Irrational numbers often arise in geometry and other branches of mathematics. They demonstrate that the world of numbers extends beyond simple fractions and decimals. Section 6. Properties of numbers: commutative, associative, and distributive. Let's learn about some fundamental properties of numbers. These properties are crucial in understanding how numbers interact with each other in various mathematical operations. These properties are like rules that always hold true when performing arithmetic operations. They form the foundation of many mathematical concepts and are essential for solving complex problems. Understanding these properties can make solving mathematical problems easier and more intuitive. They help us see patterns and relationships between numbers that might not be immediately obvious. Commutative property. This property states that the order in which we add or multiply numbers doesn't affect the result. For example, in addition 2 plus 3 equals 3 plus 2. Similarly, in multiplication 2 times 3 equals 3 times 2. This property is very useful in simplifying calculations and solving equations. Associative property. This property deals with grouping numbers in addition and multiplication. It states that the way we group numbers doesn't change the final answer. For example, in addition 2 plus 3 plus 4 equals 2 plus 3 plus 4. The same principle applies to multiplication. Multiplication 2 times 3 times 4 equals 2 times 3 times 4. This property helps in breaking down complex problems into simpler parts. Distributive property. This property connects multiplication and addition. It states that multiplying a number by a sum is the same as multiplying the number by each addend and then adding the products. For example, 2 times 3 plus 4 equals 2 times 3 plus 2 times 4. This property is particularly useful in algebra and helps in simplifying expressions. These properties are essential tools in algebra and other areas of mathematics. They provide a framework for understanding how numbers work and interact with each other. They help us simplify expressions and solve equations efficiently. By mastering these properties, we can tackle more complex mathematical problems with confidence and ease. These properties are not just theoretical concepts. They have practical applications in everyday life. From calculating discounts to solving puzzles, understanding these properties can be incredibly beneficial. So let's embrace these properties and use them to our advantage in our mathematical journey. They are the building blocks that will help us unlock the mysteries of numbers and equations. Section 7. Prime and composite numbers. Building blocks of numbers. Prime numbers are like the superheroes of the number world. A prime number is a whole number greater than one that has only two factors, 1 and itself. For example, 2, 3, 5, 7, 11 and 13 are prime numbers. They are divisible only by 1 and themselves. Composite numbers, on the other hand, are whole numbers greater than 1 that have more than 2 factors. For instance, 4, 6, 8, 9 and 10 are composite numbers. Prime numbers are incredibly important in mathematics, especially in cryptography and coding. Section 8. LCM and HCF, Finding Common Ground. LCM stands for least common multiple, and HCF stands for highest common factor. These concepts are useful for finding the smallest common multiple and the largest common factor of two or more numbers. LCM. The LCM of two or more numbers is the smallest number that is a multiple of all the given numbers. For example, the LCM of 4 and 6 is 12. HCF. The HCF of two or more numbers is the largest number that divides each of the given numbers without leaving a remainder. For example, the HCF of 12 and 18 is 6. We use LCM and HCF in various situations like adding and subtracting fractions, simplifying ratios, and solving problems involving time and distance. Section 9. Decimal representation, terminating and non-terminating decimals. Decimals are a way of representing numbers that are not whole numbers. They allow us to express values that fall between integers, providing a more precise representation of quantities. They are based on the powers of 10, which means each place value represents a power of 10. A decimal point separates the whole number part from the fractional part. making it easy to distinguish between the two. Terminating decimals. These decimals have a finite number of digits after the decimal point. They come to an end after a certain number of decimal places. For example, 0.5, 0.75, and 2.25 are terminating decimals. These numbers are easy to work with because they have a clear end. Non-terminating decimals. These decimals continue infinitely after the decimal point. They never come to an end, extending indefinitely. They can be further classified into two categories: repeating decimals. The digits after the decimal point repeat in a pattern. This pattern can be a single digit or a group of digits. For example, 0.3333, where 3 repeats, and 0.142857142.857, where 142857 repeats. These repeating patterns can help in identifying and working with such decimals. Non-repeating decimals. The digits after the decimal point do not repeat in a pattern. For example, pi, which is approximately 3.14159. These decimals are often encountered in mathematical constants and measurements. Understanding decimal representation is crucial for working with real-world measurements, performing calculations involving money, and solving problems in various fields. Mastery of decimals is essential for accuracy and precision in everyday life and professional